Hey guys, we're going to be talking about integration with ln today. And the important formula that we're going to be working with through all of our examples is going to be this integral of 1 over x dx is equal to ln of the absolute value of x plus c. So why does this happen? Well, let's look at an example. What if I told you that f of x was equal to the ln of the absolute value of x, and we wanted to know what the derivative was? Well, the ln of the absolute value of x is actually a piecewise function, and we'll talk about why that is. So it would look something like this: ln of x if x is greater than 0, and ln of negative x if x is less than 0. And let's think about the numbers that we could plug in here. So we know that from our work with natural log functions, the numbers that we could potentially plug in here would have to be greater than 0, because ln of 0 doesn't exist, ln of negative 1 doesn't exist, ln of negative 2, etc. So that's why this piece is there. We need to make sure that there is a positive value that's greater than 0 going into this argument position. Down here, if we have ln of negative x and we're told that x is less than 0, well, that means that we're plugging in any negative value. So negative 1, negative 10, negative 20, whatever it is. And when we plug that in here, that actually produces a positive value, because if I plug in a negative 20 here, that's really telling me I have ln of negative 20, which gives me a positive, so that'd be ln of 20. So what is the derivative of this then? So let's take this in pieces. So let's just do this top line here. Let's do the derivative of ln of x if x is greater than 0. Well, we know that the derivative of ln of x is just 1 over x. Okay, well, what about this other piece? What is the derivative of ln of negative x? Well, I know that from using my chain rule, because I have something on the inside here. My derivative would be 1 over negative x, and then I would have to multiply by the derivative of the inside stuff. Derivative of negative x is just negative 1 if x is less than 0, which would simplify to, again, 1 over x if x is greater than 0. That doesn't change. 1 over negative x times negative 1 is just 1 over x. So that's why that absolute value piece exists here, because no matter if we're taking the derivative of ln of x or ln of negative x, it's going to produce 1 over x no matter what. So let's take a look at some examples using this formula. We'll start off with something pretty basic. So let's do the integral of 1 over x plus 5 dx. So we've got a fraction, we've got some stuff going on in the denominator here. And whenever I see that, I automatically think to myself, okay, well, maybe I can use u substitution here. So I'm going to set u as that stuff in the denominator. I'm going to say that's x plus 5. I'll find my du, which is just going to be 1 dx. So when I go to substitute in up here, that's going to tell me that I'm going to have the integral of 1 over u, and then dx is equivalent to du. So 1 over u times du. And the integral is telling me that whenever I have 1 over something, 1 over x, 1 over u, my setup is going to be using this ln of the absolute value of x plus c. And again, I'm using that plus c in this case because I have an indefinite integral. So that's going to tell me that this is going to be equivalent to ln of the absolute value of not x, but u, since we're working with u, plus c. But I need to go back and plug in what my u stuff is. So this is going to be the ln of the absolute value of x plus 5 plus c. Well, what if I wanted to make that into a definite integral? So say I put some values on my integral. So let's say this was from 1 to 2 of 1 over x plus 5 dx. So my u substitution is still going to look the same, but remember that when we're doing the u substitution and we have some values here, I'm going to go back over to the u is equal to x plus 5, and I'm going to go ahead and change my starting value, my ending value on my integral. So when my x value is 1, 1 plus 5 is going to give me a 6. When my x value is 2, 2 plus 5 is going to give me a 7. So these values are actually just going to be from 6 to 7 of 1 over u du. So when I go to evaluate, that's going to still give me the ln of the absolute value of u. I don't need the c here anymore because I've got values here, but I want to evaluate from 6 to 7. So using the FTC, that's going to give me the ln of the absolute value of 7 minus the ln of the absolute value of 6. And I can simplify this. Absolute value of 7 is just 7. Absolute value of 6 is just 6. So ln of 7 minus ln of 6. If you want to use your calculator, that would be approximately 0.154. All right, so let's do a little bit of a different example here. So let's do the integral of x over x squared minus 3 dx. So same idea here. I'm seeing that I have now stuff in the top and the bottom. I like to generally look in the bottom of the fraction to decide what my u is going to be. So I'll set u equal to x squared minus 3. That's going to tell me du is equal to 2x dx. And when I solve for dx, my dx is going to be du over 2x. So go back up here to my integral, keep the x in the numerator. I'm going to turn that denominator into u, and then my dx is du over 2x. And here I'm noticing that my x's will cancel out. So what I'm really left with is the integral of 1 over 2u du. But we're noticing here that there's actually a constant kind of hidden in here. So I'm going to pull that 1/2 out. And what I'll be left with inside the integral is just 1 over u du. So it's going to give me 1/2. I'm going to take my integral of 1 over u du. So that's going to be ln of the absolute value of u. And I do need my plus c here because we are talking about an indefinite integral. And then I'll go ahead and substitute back in what my u value was. So it's going to be 1/2 ln of the absolute value x squared minus 3 plus c. All right, let's throw some trig in there now. So let's look at the integral of cosecant squared x over 1 plus cotangent x dx. All right, so I'll set my u as my denominator stuff, and I'm noticing that my denominator stuff contains a cotangent, and I know that its derivative has something to do with cosecant squared, so that should be a good indication that you're setting u equal to the correct value here. So I'll say u is equal to 1 plus cotangent of x, take my derivative. Du is actually equal to negative cosecant squared x dx. So when I solve for dx here, that's going to give me du over negative cosecant squared x. And then I'll go ahead and go back up to my integral over here. So carry over my numerator of cosecant squared x. My denominator is turned into u, and my dx is du over negative cosecant squared x. And here, this is going to work out pretty nicely. My cosecant squared of x's end up going away. I'm left with negative 1 over u du. Again, be careful of that negative. Don't drop that. I'm going to pull that as a negative 1 outside of the integral. So I'm left with 1 over u du. Go ahead and evaluate that. So that's going to be negative 1 times ln of the absolute value of u. I'm going to put my plus c here because, again, I'm dealing with an indefinite integral. And I'll go ahead and plug back in my u stuff. So negative ln of the absolute value of 1 plus cotangent x plus c. All right, and we will look at one more example. Let's bring in this e stuff. So let's evaluate, let's do a definite integral. So from 1 to e of ln x over x dx. All right, so here I'm wondering, okay, well, what do I set u equal to? Usually I like looking at the denominator, but the denominator is pretty simple here. So I'm going to actually set my u equal to my numerator stuff. So let's see what happens. So u is equal to ln of x. My du, my derivative of ln of x is 1 over x dx. And when I go ahead and solve for what dx is here, I can go ahead and multiply both sides by x to get rid of that. So my dx is actually x times du. Let's go back up here to the integral, and I'll leave off my starting and ending points for a second. So what that's going to give me is I've set u equal to ln of x over x times my dx is x times du. So here, this one's actually going to work out pretty nicely because my x's end up going away here. But again, don't forget that we do need to figure out what these values are. Since I'm using u substitution, I'm going to go back to see what I actually set u equal to. So my starting value here was 1. So this is asking me to do ln of 1. ln of 1 is actually just 0. So that means my starting value here would be 0. And then I want to figure out what ln of my ending value is here. So ln of e, well, ln of e is actually just 1. So I'm actually integrating from 0 to 1 of u du, if I simplify this a little bit. So this actually doesn't end up using ln anyway, because I'm just left with a nice integral here. So the integral of u is actually just 1/2 u squared, and I'm evaluating that from 0 to 1. And again, I don't need the plus c here because I have a starting and an ending value. So using FTC, that's telling me I'm going to do 1/2 times 1 squared minus 1/2 times 0 squared. So 1/2 times 1 squared is just 1/2. 1/2 times 0 is just 0. So this actually just ends up being 1/2. All right, so it's your turn to do some practice problems. Let us